statistical physics. It's an honor for us to have as a speaker today Stefano Zapperi. He's full professor at the University of Milan. He's an old friend and also a member of the society. That's important to underline. We are very proud of it. And so Stefano is also the coordinator of the Center for Complexity and Biosystems at the University of Milan. He got his degree in University Sapienza and the PhD in Boston University. Then he had a postdoc in École supérieure de physique chimie industrielle in Paris, and then came back to Rome for some years, and then finally he moved to Milan with his academic position. He received many prizes during his career for his outstanding researches, in particular in the defects dynamics, statistical physics model for defects dynamics in solids, and also for many other interdisciplinary applications of statistical physics models and concepts. So among the most important prizes, he received the Marie Curie Excellence Award, the Humboldt Research Award, and he is a member of different international academies. He's fellow of the American Physical Society, and is distinguished professor by the Academy of Finland. So we are, it's an honor for us to have his talk today. Sorry, I have some, sorry. So the colloquium today, the title is Disordered Mechanical Metamaterials. Just as an information for everyone, just last year, Stefano published an important review on Nature Review Physics about this theme. That is very, I read all the review. I found it very interesting and as an important guideline for this new field of application of statistical physics. So please, Stefano, I give the words to you. So go on.
Thank you very much, and thank you very much for the invitation. It's a pleasure to be here with among many old friends and many collaborators, so that's very nice. And let me try to share the slides. Let me see, slideshow. So, okay, 1 second, I have to kill something because my computer is using too much memory, because as usual I am...
too many processes, but we see very well.
Yeah, but it's complaining, so that's why I had to do it. Now I hope it's okay. So, today I'm going to discuss about disordered mechanical metamaterials. And this is some work that I've been doing in the past 10 years, starting with the NEAR-C grant that was mostly on mechanical properties of material. Then I got a proof of concept grant that was devoted to this disordered mechanical metamaterials, mostly on the application side. And most recently, I participate to European Innovation Council grant on applications to biological foam metamaterial for applications to architecture. So I will try to give you a little bit of overview of what I've been doing in the past 10 years on this particular field. So let me first discuss the issue of order and disorder in the context of metamaterials. So what are metamaterials? So metamaterials are, let's say, structures that have been designed for a purpose to having a certain function. And the way we design it is by creating a geometry. So the material itself is not so important. What is really important is the geometry that we use. And the geometry creates the function. So here in the middle, you have this movie by Katia Bertoldi and co-worker, and this is a classic example of an auxetic material. So you see, it's a rubber, and when you compress a rubber ball, you expect it to expand. That's what a rubber sheet would do. But in this case, they have put some holes into into the sheet, and the holes create this strange effect that we call auxetic, and we'll come back to this auxetic property. So the Poisson ratio is negative. So this means that the sheet essentially contracts while compressed, no, on the lateral direction. And this is the effect that is created by the metamaterial. Another example is this pentamode material that you see with label A. Pentamode material are particular material that have no shear modulus, but they are solid. So, and this is created by arranging the cell in a particular form. So there are countless applications of these metamaterials, but typically, if you look in the literature, most metamaterials are conceived as a unit cells that is repeated. So they are periodic, they are very ordered. On the other hand, many of these metamaterials with this function are inspired by biological objects, because biology creates structures, typically, and these structures have peculiar properties, like the bone. The bone is particularly tough, so it resists fracture, and this is for good use. But the structure of the bone is very disordered and also hierarchical. So it looks like a metamaterial, so the geometry creates the function, but it does so in a very disordered way. Here also is a seed. Sorry, there is a microphone open.
So please, who has the microphone switched on, please switch off.
So in seeds, on the other hand, you also can have interesting structure like this. This is a tobacco seed and has these interesting puzzle cells, which have a mechanical function, as we showed in a paper that I'm not able to discuss here. But so again, it's a puzzle structure. It's also disordered. So we have on one hand in metamaterials a lot of ordered structure that are designed to have a certain function, and often they are inspired by biological structure, but biological structure are almost always disordered. So this, I think, poses a set of interesting questions. First, I would like to show you some example of material that we designed, metamaterial that we design coming from biology. And this is inspired by a particular plant, carnivorous plant, that is called Drosera capensis. And you see it here. So there was a prey, in this case it's a drop of milk, that was placed in the plant. And what the plant does, it falls upon the prey and digests it. Now, this video is much accelerated, so it takes 20 minutes or 30 minutes to do this process, but it's clearly an active motion. And the question is, how does this happen? This plant is very interesting, has been studied for many years. Actually, even Darwin discusses it in its book about carnivorous plant, but the clear mechanism was never explained. So to understand how it worked, we looked at the structure, actually not myself personally, but our biologist collaborator, the group of Caterina Laporta, did all the experiments. So what they did is first they analyzed the structure, and they noticed some geometrical inhomogeneity. Typically, this is the leaf, it's a transverse section of the leaf. You see the lower cell have larger cells than the upper ones. So you see an asymmetry in the geometry, in the structure. And this is independent whether you have a closed leaf or an open leaf. So this geometrical structure is always there. It's not changed by the bending, by the closing. On the other hand, they observed a typical hormone, plant hormone, that is typically associated with shape changing in plant, which is called auxin. And what they saw is that this auxin was much larger when you had a closed leaf, when the leaf was closing. So this was indicating that indeed there was some effect of this auxin, but it was clearly homogeneous. So there was no difference between upper and lower. So it's not a differential distribution of this auxin signal that creates the bending. So the reason then must be the combination of asymmetric geometric structure plus homogeneous signal. And what auxin does is to loosen up the walls of the cells in the plant. So we put this ingredient into a simple structure. So we recreated a structure like the one in the plant. And then we we give it a symmetric, homogeneous Auxin signal, so we loosen up all the cell walls. And the result was that indeed we see bending of the structure. And this is a finite element simulation. So this inspired the metamaterial, in which we have a symmetry between bottom and top, and an homogeneous stimulus, which could be like a pressurization of these cells, or just a pressure, an uniaxial pressure on the structure. And this creates bending as a function of stress, of compression. In simulation, but also we showed it in experiment by realizing these cells. In this case, we didn't explore the disordered nature of the metamaterial, but we get inspired by the plant. On the other hand, the plant is disordered, our structure was ordered. So this inspires a set of questions, this issue of order versus disorder, that we would try to answer. And there are three classes of questions that I want to discuss today. So the first question is, how does disorder affect the metamaterial function? So if you have an ordered metamaterial and you start to add disorder to it, does this change the function in a significant way? So is it a problem or not? The second question is, are there new functions that you can find from disorder? So you have the ordered structure, now you make it disordered. Can you get something new? So not just a disruption of the function. And the third, which I think is the most interesting one, and is what I'm currently also working on, is can we create optimized functional metamaterials that are disordered? So can we imagine a way to generate disordered metamaterials with some interesting functions? And this, of course, recreates a little bit what nature is trying to do through evolution, so create structure that have a certain function that is somehow optimized for the task. So let's move towards this goal, but first let me tell you my playground. So how do I do that? And in general, what we do is work with elastic networks. Not all metamaterials are elastic. Now we're talking about mechanical metamaterials are networks. You can imagine objects like the sheet with holes. That's not really a network. But I will concentrate here on elastic network, which is a broad class of metamaterials. So in general, we'll work on 2D or 3D networks. So you see these two examples. It's a random essentially, these are random lattices and not really scale-free networks or anything of the sort. Mostly we deal with random lattices. So here is a 2D and is a 3D. Now, this is what represents the topology, but topology is not all. Actually, it's just a small part, because we really want to capture the elastic interaction when we study mechanics. And unfortunately, this is not just spring and balls, because that would miss most of the physics, but we have to take into account all the interaction. And this can be done either by a simple, this is more physics-inspired discrete element model in which we have stretching. So that would be your spring, linear spring. You have in most models that physicists use. But then, as polymer physicists do, we also want to have bending. So the fact that we can flex the structure, and we simulate bending by adding angular springs. And then also we want to have torsion. And torsion we simulate by dihedral spring. So these are typical, let's say, interaction terms that polymer physicists use. So, and we borrowed from them. But then we also use a different class of models that is more engineering, mechanical engineering inspired, which is the beam model. So now every element is not a set of point nodes connected by all these springs, but it's a full elastic body, 3D elastic body, quasi one-dimensional, which is a Timoshenko beam. And a Timoshenko beam can undergo stretching, again, or compression, bending, and torsion. So you do a torsion of the beam, and all this is represented by a stiffness matrix. In this case, it's a 2D stiffness matrix, just 6 degrees of freedom. In reality, when we do 3D beam models, we have a much larger one, but it didn't fit into the slide, so I just showed it 2D. So it's quite complicated, looking quite complicated, but it has a big advantage. It's a linear problem. And the linear problems you can solve easily on the computer, so you don't have to do complicated optimization. You just invert the matrix and you have the solution. And nowadays, with fast computers, this is very fast. So two different schemes, I will use either one or the other in the following. So now let's first look at the first question. So the effect on disorder on metamaterials, and I start to look at this disordered auxetics. So auxetic metamaterials are materials that when you compress them, they expand, and when you stretch them, when you compress them, sorry, they contract, and when you stretch them, they expand in the lateral direction. And a typical example of these kind of materials are these bow tie lattices. So they look like this. And these bow tie lattices, they have this auxetic property, so negative Poisson ratio. And what we did in this paper, together with some collaborators almost 10 years ago, is scramble a little bit this perfect bow tie. Here is a little scrambled. Here is even more scrambled. And the difference between left and right is that here we also introduce some topological defects. Here, they're all cells that have 6 edges. Here, you start to have cells with 5, with 7, and so on. And then you can quantify by some parameter delta how much disorder you put or how much fluctuations you have in the material, in the metamaterial. And then we studied mechanical properties both by simulation. In this case, simulations were done using this polymer physics model, but also by printing in 3D this structure and doing mechanical tests. So, and at the end, what we see is that Poisson ratio for 0 disorder, you get the nice auxetic behavior, minus 0.9, but then as you add disorder, you change a little bit the Poisson ratio, so you lose a little bit of this nice auxetic behavior, but not so much. At some point, however, there is a big loss of this negative Poisson ratio, so the Poisson ratio becomes much larger. And what happens at this point, what we realize that what happens is that you get topological defects coming into play. As long as you don't have topological defects, so you wiggle a little bit, you still get the same kind of behavior. But when you get loss of hexagons, then you start to lose these auxetic properties in a much more stronger way. So this story, this paper just tells you that disorder is bad for you. So you start from a very nice auxetic material in the perfect lattice. You distort it a little bit. You distort a little bit the geometry. You get less auxeticity. You distort the topology is even worse. No? So topology is more important than geometry and so on. But it's all a negative story if you want. Disorder doesn't help. Then we looked at another problem, which is a disordered beam lattice. And here, this is an example of something where introducing disorder creates something new with respect to the ordered lattice, not just worse, but different. And here is the typical structure we understand, we look at. The idea is to have lightweight architectures. And this is a classical problem that predates even the invention of metamaterials. Here is a paper of 2006, but there are papers even 10 years earlier than that, and made by Ashby and Gibson is another name. And they were concerned with the properties of foams and general lattices, lattice structures. And the idea is to have objects that have a certain elastic property, so like the Young modulus, so it's typically the stiffness of the material, and you want them also to be very light, no? So with as less material as possible. And what they found by looking at this structure of various types, foams and so on, is that the Young modulus typically has a scaling function with the density. So the heaviest it is, of course, the stiffer it is. And it does so with a power law. The power law, though, was easy to explain at the time. And you have that typically, you can do it in 2 dimensions, in 3 dimensions, is that when n equal 1, this means that mostly elasticity is controlled by stretching. So when you pull or when you compress, it's stretching what matters. On the other hand, when bending is dominating, so you don't have so much stretching but bending, then this exponent n becomes 3 in 2 dimensions and 2 in 3 dimensions. So you have, if you want, in the language of statistical physics, we have 2 universality class with sort of trivial exponents, n equal 1 or n equal 2 in 3 dimensions. And one is associated with mostly stretching and the other with mostly bending. And this is, of course, all this was done having simple periodic structures in mind. No? Either you stretch it or you bending, depending on the unit cell. Now we wanted to look at what happened in a disordered context. And so we have here a typical percolation type scenario where we have a perfect triangular lattice. So the perfect triangular lattice, now we're in 2 dimensions, behaves like a stretching dominated. So when you compress it, when you stretch it, it's stretching of the single beams that matter. Or when you compress it, it's the compression of the single beam that matters. So the exponent is 1 indeed. Even if you start to remove bonds, no? Like you do in percolation, you get stretching dominated behavior. On the other hand, if you start to remove a lot of bonds, here is the panel C, now what you see is mostly bending dominated, so exponent n equal to 3. So this is typically means that when you pull, you start to bend the lattice because the connectivity is not rigid, essentially. You are above the rigidity percolation transition, so you see bending more than stretching. But what is interesting that was not known is that when you are in the middle between these 2 regimes, so below the rigidity percolation threshold but close to it, then you start to get a new exponent, an exponent of 2, which is neither bending dominated nor stretching dominated. And we can try to create a sort of phase diagram. On one axis, we have the probability, like the percolation probability. Of course, there is a PC. This is the percolation probability. Here, there is no stiffness at all. I mean, there is no connection, so there is no stiffness. So it's not very interesting. But you have a stretching dominated phase when you have a lot of bonds, so that it's fully connected. A bending dominated when you have less bonds. And then a mixed phase. And the mixed phase is around what is known as the rigidity percolation transition. Of course, the rigidity percolation transition you define when you have just springs, no? But here these are not springs; these are Timoshenko beams. No? So it's slightly more complex from the mechanical point of view. So what it's just a rigidity transition in a spring network becomes another type of transition that you can read off from the stiffness scaling, and here this parameter A is like the width of each of these beam, which also plays a role. Then we checked another thing, not just the elastic stiffness, but also the buckling force. So if you take a slender structure and you crush it, like try it with a spaghetto, you push it at some point, it doesn't compress, no, very soon it doesn't compress if it's slender, and it buckles, no, it goes out of plane. And there is a force at which this happens, so like a critical strength for buckling. Now we're talking about compression, and here we find 2 different scaling laws. For the bending dominated, we have exponent 0, so it doesn't scale with the density. For the stretching dominated behavior, we have exponent 2, and then we get a new exponent around 1, of course wiggling a little bit here, but which is a mixed phase close to the rigidity percolation transition. So new sort of universality classes that is induced by disorder, a mixed phase between stretching and bending. So these, all these, and we have some scaling relations. We have derived some scaling relation to try to, because these are very simple exponents, to try to derive these exponents from some simple generic laws. But you can read about that in the paper if you are interested. So this is then an example after a first example where disorder was just removing the interesting property. Here, disorder creates a new kind of scaling that was not present either in the ordered system, either for let's say high connectivity, stretching dominated, and low connectivity, bending dominated. But there is a mixed phase where the connectivity is sort of disordered, where you get a new kind of scaling. Now we come to the most challenging part, is to design disordered metamaterials. And in this case, I'm concentrating mostly on actuators. So materials not just auxetic, but materials that have a particular function. And so if you want to understand what I mean by actuator, is something simple that change in some way tries to transform movement or displacement. So, and the simple example is a door lock. So what is a door lock? Just stripped to the bone, is something that transforms a mechanism which you pull down into a transfer motion in the lock. No? So it transforms the motion. And typically these door locks are made by many pieces that are assembled. So what this has to do with metamaterials? Well, this has nothing to do with the metamaterials, but one could imagine a door lock that instead of being assembled by different pieces, it's just created in one piece and 3D printed. And actually, I didn't have to imagine this because somebody did it. These people in Potsdam 10 years ago, they invented this metamaterial door lock that was designed to do exactly what the door lock does. So just by placing the cells in right places. Of course, this is just something that you design. You sit down and think of how to do it. But we would like to do it differently. We'd like to have an automatic design. So we want to first imagine what we want, and then create the structure that does it. And in this case, for instance, I do something very simple. I would like to push here, and I would like as an output that this part, that the part on the left, moves sideways. So that's my simple kind of actuation. So change the motion. So I push on one side and I displace on the other side. And of course, I would like to maximize this output for a given input. And I want to deal again with metamaterial structures. And what our plan works like following. So we want to do a minimization of some cost function, and we do that by simulated annealing, which I guess most people in statistical physics are familiar with. So it's a Monte Carlo procedure that deals with a temperature that changes in a clever way. So how does it work? We start with a lattice like the one here, so triangular lattice, for instance, and then we start to add or remove bonds. At the beginning, we just remove, then we can add more bonds. Then, whenever we have removed the bond, we solve the elastic problem. Again, if these are beams, this would be inverting this stiffness matrix for the entire problem for a given boundary condition. And the boundary condition here is just the force that we impose, for instance, the fact that we push on the top. And then we measure some efficiency. In this case, the efficiency is just the ratio between the input displacement versus the output displacement versus the input displacement, so what we want to maximize. And then we create a cost function, in this case, the exponential of that, which we try to minimize. And we do that as if this was an energy, and we do a sort of Monte Carlo, in this case simulated annealing, until we find some structure that we like. So you see this structure here is moving to the left as it's been programmed to do. So in this case, we don't design the structure ourselves, just thinking what's the best strategy, but we let the computer do it in typical statistical physics way. And okay, these are the trajectories, so we can try different times and then see different stories. And for instance, at some point we get something that we like this green line here, and a very high efficiency. And so we may want to take that one. Once we have it, we can for instance, look at it and make some finite element simulation of it to see, for instance, that there are high stress regions. We may want to correct for that, but okay, that's another step. But then at the end, we can check if what we produced makes sense and whether it does the actuation that we programmed by 3D printing the structure. So this is a bit the plan, and we can do it for different type of things. For instance, we could imagine to create pliers, and we want to maximize the force here at the center as a function of the displacement, input displacement. And here the interesting thing is that the same people who did the door lock, they had already designed a plier, and they did it not by any algorithm. They just sat down, their engineers, and they thought what a good plier could be, and they got an efficiency of 22%. Now we tried the same with our algorithm, and we can design a plier that is now 50%. So it's more efficient than the human design. Of course, to do this, we had to find something that was designed by somebody else, because if I design it myself, I might cheat a little bit and make something that doesn't work very well. Well, in this case, we try to beat something that was done by somebody else. So we can imagine that they try their best. And so this efficiency is independent, for instance, of the output of the gauge stiffness and so on. It's always better, the machine design with respect to the human design. We can also start from random lattices, like instead of starting from a triangular lattice, we can start from a random lattice, and okay, we can improve somehow the results. Here is again the same actuator as before, and typically the efficiency is a bit better when you start from an amorphous type of structure rather than a triangular lattice. Okay, you have more configurations when you are amorphous. In this case, it's not always so. Sometimes the ordered lattice is better. Like in the auxetic, you cannot beat the perfect bow tie lattice. Then we try to extend this to 3D. So there was this interesting paper in Science about these twist metamaterials. So these twist metamaterials, when you compress them, they start to twist, they rotate. And here are two structures that have been proposed in two different papers. One is the Science one that went into the cover, and this is another simpler one that was produced by the same group. And we wanted to now generate twist metamaterials with our algorithm. And so this can be done. Here is an example. This is the original structure. This is another structure that we designed by just having bonds on the sides of the cube, so on the faces of the cube. So this is just an empty cube or a full cube. And the two of them, they have better performance than the simple twist metamaterials that was proposed. Typically, they twist more for the same strain, for the same deformation, compression that is applied. So again, the algorithm can find better solutions than the one that are found by engineers. And here also we can 3D print and then test that indeed this thing is really twisting. And okay, here it is. It's twisting nicely as predicted. So at the beginning, it's not twisting because the press has to come in contact with the structure. But it's working pretty well. So it works in 2D, it works in 3D. We also thought that maybe, I mean, what is the bottleneck of all this? The bottleneck of all this algorithm is to solve the elastic problem many times. No? So you solve the elastic problem, and then you remove a bond and you continue. And solving the elastic problem is inverting a big matrix, and this is slow. So the idea is, can we use machine learning to do that? In particular, deep learning, no? Because maybe if in this way we can skip this step of computing the mechanical properties. So what we do is we feed a ResNet, so a convolutional neural network, with some images of structure, and we have this is a supervised case of learning. So we give them already the value of the efficiency, so that we have computed with the simulations, with the the mechanical simulation. And then once the neural network is trained, we want to predict the efficiency just by looking at the images. And this works quite well. So in the test set, we get 97% 0.97 R square, so it's very good. You see, this is the real value, and this is the convolutional neural network. So it's the training works, and you get very good prediction. Of course, sometimes you miss, but as usual. So the question is this useful? That's the main issue. And in reality, not so much, I would say. So there is a lot of literature now about the use of artificial neural networks in metamaterials design. And I would argue that it's not very efficient. Why? Because to generate the training set, you need a lot of simulations. And what you get doesn't generalize so well. So, of course, it works. You train and now it works. But isn't it faster if you want to know one particular structure? Isn't it faster just to do the optimization? And indeed it is, because the training takes so long. And takes so long, and it's not easy to generalize. And this is seen here. So here is a move evaluation by neural network. So now I don't solve anything. I just use the neural network that I've trained, and so I give him a structure, and I want to say, what are the bonds that is useful to change? I mean, some bonds, if I remove or not, doesn't change the efficiency, but some of them will. And this is what the discrete element model, so the mechanical simulation, tells you. Say the blue bonds you have to remove if you want to reduce the efficiency, and the other one, they don't do anything. And the neural networks predicts this. And so you can predict this sort of useful bonds. And so there is a good correlation between what is given by the mechanical simulation and what is given by the machine learning. But there are not so many configurations that you can load for the system side. So we could try to investigate is whether this what has been learned can be generalized, for instance, to larger lattices. And what happens is that when you try to generalize, you capture just a little bit, but the performance is much worse. So most of the time, you don't get the right results for a slightly different system. So you've trained on a small systems, and where mechanical simulation costs less, so you can get a good training set. Then you want to generalize to a larger system where mechanical simulation are more expensive, but the neural network doesn't perform so well. So you get the correlation coefficient between the real value and the predicted from the machine learning is 0.1, so quite poor. So this tells you that these neural networks are not so good in this context. So it looks flashy. You say, I don't solve mechanical problems, but usually, as far as I could see, in most examples, to generate a good training set that is useful, you need a lot of resources, and so it's faster to just do the optimization. Now, let me tell you about some couple of more examples. In this case, we want to face the issue of multiple objective optimization. So typically, in all these examples that I gave you, we have one objective, and then we want to just optimize for that particular objective. Here, we want to deal with a more complicated situation, which we have two objectives at the same time. And in this case, we want two things. We want auxetic behavior, so negative Poisson ratio, and also good energy absorption during fracture. So two different properties. It's not clear whether they work together well. So there are some papers in the literature that say that auxetics are very good energy absorber, but is that true? So we deal this with the minimization of a multiple objective in technical, we do it by this Chebyshev scalarization, and the two objectives are negative Poisson ratio and maximum absorbed energy. And so we combine these two. And here is the result. So this is in the initial configuration, I have a certain stress strain curve. So here I have a lattice, and what I do with this lattice, I pull it until it breaks. And in the initial curve, I have something like this. In the optimized, I get a larger energy. So in this case, the absorbed energy is the energy under the curve of the force displacement curve. And so, okay, I gain this. And also I can get auxetic behavior. So this is a picture of the displacement. And at the beginning is not auxetic. So when you pull, it shrinks laterally. And then in the new configuration, which is the optimized, which is also high energy absorbed, you get also inversion of the colors. So it instead of compressing, it expands laterally. But the question is, can I get both at in the same way? And there is a limit, and this is shown when you look at the absorbed energy versus Poisson ratio. All these gray lines are all the trajectory of optimization, and depending on where you start, you can either, or depending on which of the two properties you want to weight more. So there is a three parameters here, is how much this W is how much you weight each of the two properties. No, maybe you want to favor the absorption versus the auxetics, so you can do that by changing this coefficient. So in this case, there are just one coefficient, or two coefficients for the two properties. And by changing this, you can identify a sort of front, which is the best you can get, from these two properties. And okay, so this we call the Pareto front. So it's depending on where you go, which weights more, you can go either on one side or on the other side. But still, you can get good compromises. Now, of course, this side is not very good because here Poisson ratio is positive. So you want to stay on that side. And here is two examples where you rescale. It's a technical fact. We want to keep the mass constant in this optimization, and this we do by rescaling the beam width or the beam height, and they give slightly different results. Then once we've done all this simulation, we try to see whether this can be realized in practice. So we did experiments, 3D printed the structure and so on, and we can see that there's a good agreement between experiments and simulation, although they are quite different in the way they fracture. For instance, in the experiment, this exactly the same structure fractures in different places with different cracks. Why is that? Because there is a source of disorder that we cannot control, which is the disorder due to the 3D printing. So, of course, you would like to print a perfect structure, but it's not exactly perfect. So you get defects that are due to the production, and this you cannot capture. So although they look the same, the lattices, there is an extra disorder that you cannot control that creates this difference. But on average, then the kind of properties are preserved by the experiments. Let me move to another example. This is 3D. Every time I want to show 2D and 3D. In this case, the kind of thing we want to do is want to distribute the load. So we start with a lattice, and we imagine that we are indenting the lattice. And what we want is to distribute the load in a broader way on the bottom. No? If you don't do anything, it will be very concentrated on the region of the indenter, but you want to spread it. And this can have implications for impact absorption, so you want to spread all the pressure instead of concentrating in one point. And here is the structure that we simulate, and then we can also realize it by 3D printing. And this paper is currently submitted. And Andrea De Tri is the person who did all the experiments. And I have to mention all this last simulation were done by Hannes Holai. So here is simulations, and you see that in the initial structure, you get very concentrated load. In the optimized, this is the bottom plate, you get a much broader spread of the forces. And then we tested whether this is also good for impact absorption, and indeed it does. So if you do impact test, this is not an impact test, this is a quasi-static test, but just show you because I have a nice movie. But we did also proper impact tests, and indeed there is a better energy absorption for this impact, for this optimized structure with respect to the original one. So finally, last application is this collaboration that we had with Rold. What they do at Rold is home appliances, and Rajal Zulkarnain, a PhD student of mine, had one of these industrial grant, and he was trying to put the metamaterials into their home appliance for washing machines and so on. So like the door lock, so replacing their mechanisms by metamaterials, and he got some interesting results that shows as a proof of concept that you can really use this kind of optimized metamaterials into products. And with this, I would like to, Andrea was very kind and mentioned a review article with Michael Seiser on disorder mechanical metamaterials that got the cover of Nature Review Physics. We also have another one more computationally oriented with some other authors as well that was also in the cover on Nature Computational Science. So if you want to know more about this issue of machine learning, how useful it is, and optimization and so on, this is the right thing. If you want to discuss more about nature-inspired metamaterials and the role of disorder, there is this other review article. And so you can have a look at those if you want to get a more deeper understanding. Let me thank all my co-workers, so the Center of Complexity and Biosystems that over the year have worked on this, co-workers at CNR, ICMATE, who did a lot of experiments for us, Antonio Tuissi and Jacopo Fiocchi, and the people at Aalto University and at FAO, namely Michael Seiser. And finally, I would like to use this opportunity for an advertisement, completely different topic. We have a summer school in Como that we organized. It's more on social science and econophysics. It's called Advances in Complex Systems Inequality. Deadline is April 30 for PhD students and postdocs that would like to come. And with this, I'm happy to answer your questions. And I leave this in case somebody wants to come. Sorry for the advertisement, but deadline is soon.
So thank you very much, Stefano. Thank you very much. So I ask to the auditor if there is some question for Stefano. There were many stimulating aspects to discuss. So is there any question?
Well, maybe, may I ask a question?
Yes, of course.
I didn't raise my hand. Thank you, Stefano. This is really an astonishing talk. And I was wondering, from the examples you gave, especially toward the end where you can control actually the distribution of local stress in the material, I'm wondering, can you then control through topology the resilience to fracture of a material?
Yes and no. I mean, I can to a certain extent. So in a sense that we are able to optimize the absorbed energy. So in a sense, we can control the stress strain curve and give it the shape we want. We cannot do that completely because there is some form of disorder that escapes us. Because when you produce a structure, it's not only the topology, it's that each beam will have a slightly different breaking threshold, as you know, because you studied all these things very well. And this, it's hard to predict. No, it's unpredictable. Depends on the printing process.
But so we can have a very, if you don't have highly stressed locations, like you have a very uniform distribution, because usually fracture nucleates from an highly stressed element, right, and then propagates. But the nucleation is very local. So I was wondering if you can diffuse your stress distribution, then in a way you can.
That is what the algorithm is doing. Is trying to find a way. If the stresses are all the same, if the failure stress, the algorithm assumes that all the stresses are all failure stresses are all the same, and then it adjusts the topology to get you the the highest, the best stress strain curve that you want, like the one that has the highest absorbed energy. So if we do, for instance, if we don't care about auxeticity, of course we can get much better absorbed energy. And when we do the experiments where there is an extra complication that we cannot control the internal disorder, we still get it. So it works in this sense.
And you don't have the problem concerned with fatigue or this periodic stressing and so on, because if you...
We do, in a sense, we didn't optimize for fatigue. So if we want to optimize for fatigue, you have to do probably something different. No? Here is optimized for simple tensile test once. No? But if you want to do fatigue fracture, you have to model fatigue, optimize it, and it's in principle doable. Okay. And we are doing also stuff like that, yes.
Impressive, thank you.
Thank you. Is there any other question? If not, I have a question. Because what you showed during the talk is clearly how we can optimize some property of the metamaterials by increasing the disorder, but the connections in the materials are always local.
Yes.
Yes, but more or less you start from a lattice or something like that, and you start to dilute, etc.
Like either a lattice or a random lattice, yes.
Or a random lattice, but with local connection. So in particular, in the 3D case, have you investigated what happens if you add some long-range connections?
But in real life, long-range connections are hard, no? Because they
are hard, but in 3D they are possible.
No, they are possible, but you don't want to have intersections. And
no, yes, I know. That's about
since all these structures are very dense, long connections also are weaker from the mechanical point of view. They will have very, very strong buckling strength. No, you know,
yes.
If you have a beam or you have a very long beam, the long beam is much weaker. So as soon as you compress it, it will buckle. So
yes.
you will be very unstable. So one can try, but not sure it will help.
My question was motivated because, you know, there is also this flourishing literature about real networks or in which they try to start from a very disordered case in which you have not local connections. And I ask it always if it is something real, realizable, and usable.
No, you can realize probably, but I don't think it's very useful.
Okay.
I don't think, I mean, my personal view, but I have very strong opinion on that random lattices are a good start for mechanical properties. On the other hand, power law networks, complex networks, a very bad start. In a sense, it will not give you interesting properties. It will be hard to manufacture. You spend a lot of time doing it, and you don't gain much. So
I agree with you. That's why I asked it.
So, and random lattice is not something new. I mean, it's very old stuff, but has been working fine for decades. So these physical networks, I think, is just my personal view, is trying to fit and find a mechanical application for something that doesn't have it.
Okay, I see. So I've seen that there was another question, maybe.
Yes, thank you. Thank you very much for the very nice talk. So I have a question about crux propagation. If I understand correctly, when you compared the simulated and the experimental results about this, you were saying that there is some difference due to the presence of defects in the experimental structure created. So are you talking here about defects in the sense of imperfection in the printing, or defects really as topological defects?
No. Topology is exactly the same, because we printed exactly the structure that we generated. The problem is that when you print it, every beam is different.
Right, sure. Okay, but then, so, I mean, do you actually know whether the presence of topological defects would enhance or would strengthen or fragilize in general the structure? And do you know whether there are generic results about this?
No, I mean, it depends, no? I mean, first of all, what do you mean by topological defects? In this case, we have a lattice and we remove bonds, so essentially, or a random lattice and we remove bonds. So depending on which bonds you remove, you have different mechanical behavior. And what we try to do is to remove those bonds that will give us for instance, the highest resistance.
Okay.
So of course, if you remove the wrong bonds, you can have weaker lattices or stronger lattices. So there is not a single answer.
Okay, so there is essentially no genetic.
Okay, keep something in mind. I didn't mention, but it's an important point. In all this simulation where we optimize fracture, we do so by keeping the volume constant. So whenever we remove a bond, we make all the other bonds a little thicker. Why? Yeah, because otherwise removing bond will always weaken, no? But in a trivial way, no? But we want to say same topology, but different topologies, but same, let's say, weight, no?
Yes.
So that the other bond become a little stronger. Otherwise, it's a trivial problem. You just lose everything when you remove bonds.
Okay, thank you very much.
Is there any other question? If not, we thank very much Stefano for the wonderful talk, and we give you the appointment for September for the next colloquium. Because in 2 months there will be the conference, the national conference of the Italian Society of Statistical Physics in Parma. So please give a look to the announcement and register for the conference, apply for contributions. And so the next talk will be at the end of the summer. So thank you again to everyone, and thank you, Stefano, again.
Thanks a lot to everybody.
Bye-bye.
Coming.
Bye-bye.
Ciao.